The most close to myself is the CubeSat, which is mine. The SEAM story, and SEAM was also an EU-funded project. It has been an extremely useful experience. I will not have time to talk about everything, but I'll first introduce the objectives of the project, and then talk about the satellite concept, and then we'll speak about S-band communication, deployable boom, and I'll tell the sad story about the launch, and I summarize with some lessons learned. So, we got this project as FP7 projects, and it was actually in the SME-oriented funding program, SME for Space. The consortium consists of 8 partners, and is led by KTH. The other partners are here. So, 8 partners, 6 of them SMEs, and we are the coordinators. So what did we want to do? What we set out to do is to have a high quality DC and AC magnetic measurements on a nanosatellite. And this, of course, opens scientifically for constellations of such satellites where you can address questions in space science and space weather applications. And the challenge is that the satellite systems themselves produce a lot of disturbances, and you want to get away from them. And on big satellites, you're usually talking several meter long booms, which is a mechanical challenge. If you want to do it on a small spacecraft, you still need a boom, and that was one of the central parts of the development, which was done by KTH, my colleagues in mechanics. A part of this science goal, we have 2 technical goals. So one is a new approach to operation strategy. I will discuss that a bit later, and the other is high TM-TC rate. You should remember this was 2013, so what is high there may be not as high at the moment, but also the concept of using commercial ground stations on affordable basis. So the idea is that we would be using the available time on ground station networks, which we would book at low priority, so that we don't have reserved passes just for us, but we could go in the slots which are available. This requires a certain degree of autonomy on the spacecraft side, so that we can leave without pass or handle passes when they are given opportunity. The commercial ground station, they have big customers and they are not very much interested in doing specialized things. We must comply with the CCSDS standard. What we can see with a DC magnetometer, the auroral currents, this is just a demonstration from an Iridium satellite with very lousy magnetometer, but you can still see this is the orbital latitude, and then there are 6 satellites in the plane. If you align them all, even with a 50 nanotesla resolution, you can still see these 2 rings of currents around the poles. Okay, so northern hemisphere, southern hemisphere. And these auroral currents are manifestation of the aurora, and you can only see them from space in this way, and if we have good magnetometer, we can monitor them. This was the DC magnetometer. In our case, it would go to 20 kilohertz, so it's emissions between 50 hertz and 20 kilohertz. The most prominent are whistlers. The Whistler emissions were discovered already before World War II. In the radio band, you could listen in the audio frequencies, and if you just convert it into sound, you would hear the whistling falling tones. And this is a lightning-produced pulse in the opposite hemisphere, which is dispersed by propagation in the magnetosphere. And this dispersion tells us a lot of the conditions of the propagation. Basically, you can get the density. This is one of the topics. Then aurora produces also some interesting waves. So those features are something we can monitor. And another somewhat new topic is anthropogenic emission, or emissions produced by people, and the observation of 50 hertz and 60 hertz from power lines in the ionosphere, which should not really be getting there because it's very low frequency, but it's still observed. But more strangely, on occasions, observations of harmonics of 50 hertz, which are centered about quite high frequencies. So it could be in the kilohertz range, you have a staggered 50 hertz harmonics. And this is not quite understood, but this is something we could cover. So we set out with a concept. If we have a long boom, it actually helps to stabilize the satellite by gravity gradient. Then if we want things magnetically clean, we don't want any motors. We go for magnetorquers without the core, because the core itself magnetizes. So it's air-wound magnetorquers. And this is quite a distributed system. We will see in a moment the schematic. And we went to huge extent to make the satellite magnetically clean. and remove the sensors on the tip of the boom. So what's inside? This is quite early diagram of the satellite. We have a search coil magnetometer. There are 3 analog signals. There is an electric field sensor, which is basically 2 exposed conductive plates on the tips of the boom, which are used as a dipole antenna in low frequencies. And then there is a flux gate magnetometer, low frequency. And then there is a star tracker, 1 on the boom, 1 on the body. And there are DPU, okay, data processing unit, mass memory, and S-band receiver. And then here we have all the service systems which are needed to keep the thing running. All of the service systems come from GomSpace, and those are the GPS, NanoMind onboard computer, NanoPower, and the UHF AX100. But in the science signal, like each unit is coming from another company. That's something which EU very much liked. And we liked it in the end, but it was a challenge to make things work. That's just another view from these early days. We have OBC, and then we have 1 dedicated I2C bus for the sensors, which are just for ADCS, and then everything else sits on the I2C bus. And this was the early allocation. In the middle, we have the deployable boom with 1 search coil sensor on 1 tip, the flux gate sensor on another tip, and then we have 1 U occupied by GomSpace systems and 1 U occupied by all the payload systems. UHF antenna and deployable solar panels. This is a few months later, this preliminary CAD, how things look like. So in the end, the system became slightly more complicated, okay? So this is basically the same diagram. If you look for differences, what you can see is that all the platform actually goes on the CAN bus, and then 1 OBC suddenly has become 2 OBCs. So we have mission OBC and we have ADCS OBC. And the reason here for splitting the onboard computer into 2 was not really performance. So I think functionally, or in terms of performance of OBC, we could squeeze both of them into 1. But in terms of development, it has been a huge relief to kind of be able to focus on the mission software in 1 OBC and ADCS in the other OBC. But the details, if you come to building it, are even more involved. So this is another diagram of the same thing, focusing on which units are there and which are interconnected. We made lists and tables, and we have like 101 connectors which need to be connected, not counting the ones which are already pre-connected inside. And there are 40 cables. And that's returning to what Leonardo showed. You have a nice CAD, and then you have a picture of the thing, and the cables look like a mess. So that's something to consider. So, data flow. The satellite objective is to collect science data. So we have the sensors, we have the DPU, and the DPU and the raw waveform is 2.5 megabit per second for the AC magnetic field data and 24 kilobits per second for the DC data. And we have no chance to transmit everything, not even on S-band. Okay? So what we do, we produce on board some quick look data, and then this quick look data takes much less space, and we can download those and decide what to request of the complete data. And then we have all the auxiliary data, attitude, orbit. These are handled by the OBC, and these are stored here. Description of the quick look data, decimated data, some frequency spectra which are taken at low cadence allow us to see this quick look and then prepare which data would be sent down on the next downlink. Okay, so this is another view of the operations. We have 2 communication systems. We have UHF communication system and we have the S-band. So UHF is AX100. We may have at best something like 20 kilobits per second, so there is no chance to put any of the science data through that. So this is mainly for keeping the platform alive, but the science data goes through the S-band. And the S-band goes to the ground stations of what used to be called Prioranet. It's a network of ground stations operated by SSC. So the big hub is S-Range near Kiruna, but they also have stations in Santiago, in Australia, in Canada. It's really a global network. And they have a receiver, which is a commercial receiver called Cortex. It's standard. They know that it works, and it is fully compliant with CCSDS standard, which means that we have to be fully compliant with the CCSDS standard as well. We download, we have a mission control system developed by SSC and OHB, which is called Ramses. So we look at real-time housekeeping, we look at quick look, and this goes as a command. And on the next downlink, this high resolution data has been copied. Yeah, so this is the nominal operations that they would be. So we would upload the operation schedules, when do we want to run in which mode, and then upload the high resolution data requests, and then download all the data which were prepared earlier, which would be the stored housekeeping data, the quick look data, and then raw data which has been copied earlier. So these both things are doable over UHF, but here we really need the high data rate. And when I say high data rate, the raw data rate of the S-band transceiver we have is 3 megabits per second. It becomes less with encoding. Now, something which whoever is a project manager here likes to see. We started it in 2013 in October, and work packages and everything, and launch was supposed to be at some point in 2016. PDR, we were quite lucky, and everything looked well, and then EU got nervous. They requested an extra review. We did the extra review, then we had the CDR. But also the launch date was already becoming more and more unclear at that point. And then they wanted another review, and then we had a review which was supposed to be a flight readiness review, but we knew that the launch was already far there. So this review was still called flight readiness review, but real flight readiness review was in September 16. Okay, I'll tell you about the launch. The launch was exactly 1 year ago, 28th of November 2017. But I'll first walk you through some things we learned, and this is both high and low, so some of them could be obvious to you, so I apologize. So design of harnessing should be given, and with harnessing I mean cables, should be given attention very early in the project, because it is extremely important electrically. It's very difficult to change afterwards, but also it is not realized by mechanical designers how much space cables may take. The cables are not easily drawn in the CAD. So we had a mock-up of them as 3D printed systems, and we made the real cable and glued real connectors where they are and tried to guide cables. And we discovered a lot of things, so we had to change a few things. If the cable is too short, then you're screwed. If the cable is too long, you may think it's okay, but you need to stock things somewhere and you need to tie it down. So it's a challenge. So the second thing, I2C bus sounds nice and simple, and it is, but if you have many units which are built in different places, even if everyone claims to be compliant with I2C bus specifications, you hook it up together and you start getting problems. This seems to be unavoidable, and either you test the physical layer communication very, very early, or you try to stay away from I2C bus, or you try to separate them. So the GSSB, the internal I2C bus of GomSpace, they didn't want anything else to be hooked up to that bus, and the other bus looked quite okay until we started connecting more and more units to it, and then at some point we realized this is not going to work. And that's why part of the platform, or all the platform communications, was shifted to the CAN bus. So we have a CAN bus for platform communication, and that works. Then with the power system, you make your power budget, but one has to be careful what happens when things are turned on and turned off. Because some systems, when you turn them on, they require a lot of current in the very beginning. These transient currents can result in a battery voltage drop, which will affect you in quite significant ways. So early system design is very important. Now I will speak a little bit more about the S-band chain debugging. So we have the sensor somewhere there. The sensors are digitized in case of the AC magnetometer by DPU, and the digital data comes from the flux gate for the DC magnetic field. And then we have a storage of 64 gigabyte on DPU, so we can store waveforms for 2 days or even more. Okay? And then some of the data, the quick looks which are produced, we want them at all times. And then the high resolution data, we want them by request. So this huge storage of data has somehow to go into mass memory. This TCM is a unit from OAC Microtech, which I think it stands for tightly coupled memory or something like that. So the function here is double. First, it's a mass memory, but it's not a simple mass memory. It's a mass memory which also prepares the formatting of telemetry in accordance with the CCSDS format. So when telemetry is pushed here, it is already being packed into these space packets with APIDs and everything. And when it has to be sent down to the S-band, it is being sent as a data and clock. So the S-band transceiver is basically a modulator. So you have your frequency modulation defined, which in this case is QPSK, quadrature phase shift keying, and you just need to feed it with data and clock. So the S-band transceiver is module, which doesn't care about content, and then all the content modulation in the baseband, the bit stream, is done here. So it's a CCSDS packets, encoding, and everything like that. And this has to be done right, because then when you receive it on this Cortex, it only understands CCSDS. If it's some special format you made up, the guys who run these big stations, they will tell you, no, we will not bother doing it. So, how did we try to test it? The original test was, so we said, okay, we have the engineering qualification model, we go to S-range for 2 days, we test it, and then we are happy, and then we have one flight model, we go to S-range, 2 days, test it, and make end-to-end test. However, we realized very early that all this CCSDS packaging was very difficult. There is no way to actually verify it other than running against Cortex. Because what you could be tempted to doing, you say, we build a system which transmits CCSDS, and then we build a system which receives it, decodes. However, if you build it yourself, and you build in the same mistake on transmission and receiving, there is a big chance that it will not work with the real receiver. And we were quite lucky that the SSC could borrow us the Cortex receiver, which is a rack-mounted thing, 20 kilograms, for half a year. And we used this half a year to debug. This was extremely useful. And then we were very optimistic. We said, we have debugged it, we know it works. So let's do a test over air with a real antenna, with a real system. And the people of SSC, they were a little bit skeptical. They say, it's not the way we do things. But why not? Yeah? The idea here was that this satellite, you can see the satellite, and you can see the SSC engineers very much amused by it. Yeah? And it was put in a box with RF shielding material. So the idea was, okay, we only transmit in one direction, we shield in on other directions. We put it on a mast, a few kilometers away from the receiving antenna at this range. Unfortunately, there were both practical problems and the real problem. So the practical problem was that you could not really run the stuff for a very long time autonomously for 2 reasons. First, if you want to run it both ways, you have to rely on the commands being received, and if that is what you're testing, that's a bit iffy. So if you don't receive commands, you don't know if it works or not. But the more significant problem was that the S-band consumes, in our case, something like 12 watts. And you cannot run it without power for a long time, and you cannot have solar panels because you sit in the box which is RF shielded. So you have a cable running in, and the cable running into a shielded box is a very good antenna. So you get a lot of interference. But the real problem was also that the mast is not extremely high, maybe 15, 20 meters, and you get some reflections from the ground, interference, and so on and so forth. So this was the setup. There was interference with metal parts, damping material not nominal, all these power cables going in, and the conclusion was, okay, we need more testing. And then this more testing was done the SSC way. And how usually the satellites are tested for RF compatibility is you have like a suitcase test. You go with the satellite or the part of it which is important in that case, and you connect it with coax cables. So you skip all antennas, you connect just coax cables. And then, of course, this implies the antenna works both on the satellite and on the receiving station. But that is a separate problem. The RF antenna on the satellite can be characterized on its own, and the ground station, hopefully they know what they're doing. So this was a test then in July 2016, and you can see this whole rack of equipment is what the SSC guys need to do the tests their way. 2 people from SSC, this guy builds the S-band radio, this guy builds the TCM. Although the telemetry and telecommand were in principle demonstrated, there were a lot of uncertainties, and the purpose here was to do it properly with a cable instead of air gap. And the full stack of equipment was brought, which includes both Cortex, up and down converters, noise generators, dampers, and so on. And this is just one test which I show you in a bit of detail. Okay, so it's a command receiver acquisition threshold. We have the SIM spacecraft, a debug connection for the S-band, which allows us to see what happens in the S-band. We have the noise source, spectrum analyzers, S-band down converter, S-band up converter. In this case, we are testing uplink, so that's S-band up converter. We have a cortex, modulator part of the cortex. Everything is on LAN. So it's a lot of equipment. They want to characterize and calibrate each cable, how much dB you have there. And then you go in power high and down, and you see where you have the acquisition of signal. And the conclusion of this one was that everything exceeds the performance requirements, everything is good. So this was just one. There are more telemetry receiver threshold test, pulse code modulation data quality test, basically looking at the bit error rate versus the power signal, command receiver sensitivity test, uplink sweep rate, and then end-to-end when you run satellite over S-band. So it took a couple of days, and most of the things actually worked out, except for the uplink sweep rate. This is an interesting test. If you build your own station, if you work on UHF, the satellite moves, so you have the Doppler shift. You have the Doppler shift between the receiver and transmitter, and you want to compensate for it. And you can do it either the quick and dirty way, or you can do it the proper way. The proper way is to have the satellite receiver actually tracking the signal. The quick and dirty way is you can calculate what the Doppler shift should be and correct for it from the ground. Something you can happily do if you have your own station. If you go to guys who run these 15-meter antennas, they usually don't want to bother, because it's another complication, and it should be the receiver which should log in on the signal, right? So the idea here is that we send not only on a nominal frequency, but also within a range of the Doppler frequencies. And then not only at constant frequency, but also at a changing Doppler shift, because as satellite passes by, the relative velocity with the transmitter will be changing, and you need to ensure that it can keep the lock. This was tested, and it was discovered that it doesn't keep the lock. Okay, so we were changing the frequency here, and then at some point it just dropped. And during the increase of the frequency on the transmitter, which was to simulate the relative Doppler, it was still detecting the same frequency with gain increasing, and then at some point it dropped. And this was a very funny bug in the software radio, which could not be detected for a very interesting reason. Because what happened, the guys in Germany, of course, did their homework. They had a generator which was generating the sweep of the Doppler, and they had the radio receiving and looking at the log, and it all worked. But it didn't work here. Why? Because the generator could not generate a continuous ramp of frequency. What it did steps. And the steps were large enough that the software would go into reacquisition of frequency, so it could jump between the frequency. But if the frequency slowly changes or continuously changes, it was not able to do the change. Of course, they fixed the bug, and then we needed another test. So go to S-range, connect everything, and test this particular one. And it was coping with 700 hertz per second and a range of 160 kilohertz, which is in excess of what you expect in LEO. So this was done. Now we switch to vibration tests and the boom, because the boom is a very important part. The way the boom works, it has bistable springs which have stored energy, and then they unroll at the same time into both directions, deploying the two boom tips. The axis of rotation is fixed in the structure inside the satellite. The problem is that the boom is not strong enough to support itself in gravity. So when you do the tests, you have to go to big extent of hassle of loading the gravity, which you can do with thin wires. This was done in a KTH building where we have a ceiling height of over 12 meters or so you could hang wires. And then you can run the test, and in this case, it is just engineering. Okay, so here the whole thing is kept by a nylon filament, pretty much as everything deployable is kept. And then if you burn it, in this case with just a soldering iron, then you can see it deploys. That's quite nice. This is a top view of the same thing. So you can see these two white things are half cylindrical tape springs. So they are bistable. They can be stable in the rolled flat situation, and they can also be stable in deployed situation. And then this harness in the middle is a flex PCB, which has all the connectivity to the sensors. And then we did a random vibration test. And the idea with random vibration test is to see that nothing breaks. And this is even more important for deployables, that nothing gets stuck. So this was done in all directions, and then it did not deploy. And why? We believe because it was not gravity offloaded, because we didn't think about suspension of the things before the test, and then after the test it's all done. You cannot do it. You need to prepare for it before. And then when it was repacked and the test done again, it deployed beautifully. So doing things by the book, it did deploy, but not directly after the vibration test. So this had to be repeated again. Also, we had another test which came in quite late. When we were already preparing to send things for launch, they said, oh, by the way, have you qualified for the static loads? No, we didn't think about it. Yeah, you should do this qualification. It's not so easy to do. So you need a centrifuge, which can give you 10G, or you need to do an equivalent vibration, which is called sine burst vibration. It looks quite violent, actually. Well, this was done, and then after that, with gravity offloading, you can see the strings there. It was deployed, so everything was good. And this is a picture of the whole boom deployed. Whenever you have deployables, it's a lot of things you need to think about, also in terms of sequence of things. Even when preparing for flight, there is a big question. Okay, we do acceptance vibration, and then we deploy, and then we repack. Do we do another acceptance vibration or not? You can think about this. Right. We were very reluctant about thermal vacuum tests because it is expensive, and we didn't have a facility to do it. We went to Kiruna, and they have a thermal vacuum chamber, and we did the test. This is the chamber. We had a table. We had a lot of sensors. Of course, we've done both vacuum tests before and thermal cycling before, and we'll see what happens. Everything was working very nicely, except that one system stopped working, failed at this moment, and we were thinking, okay, so what's going on? We could confirm the operation, we could confirm the thermal regime to the extent we knew what it should be, and we discovered an anomaly on the connector. And the anomaly on the connector was of very funny kind. This is far too technical for people who are not electronics, but it looked like the flux residue was somewhere on the connector and started traveling, okay? So the thing was, of course, soldered and then cleaned, and it was nice. The connectors were cleaned. But after the thermal vacuum test, when we opened and we looked on the connector on the microscope, we could see the flux residue which has traveled. And apparently, this is not happening in normal thermal tests, and this brought in another range of philosophical questions. For example, if you solder the boards and you clean them, how do you know when they are clean? Do you use ultrasound or not? Because if you want to clean the mechanical part, you put it into ultrasound bus, and then it gets very clean. But if you put a soldered printed circuit board into ultrasonic bus, if you ask some people, they will tell you that that's absolutely forbidden because the solder joints will become more brittle. Interesting question, okay? Another issue with connectors, whenever you have two mating metal surfaces, they should be the same. In one of the systems, one of the guys did not have connectors we prescribed, which was a tin, and he said, I put the gold one. What can possibly go wrong? And what goes wrong is when you have a contact of gold and tin, you have an electrochemical potential, and it promotes corrosion extremely much. Even if you are in a clean room environment, in dry environment, it will corrode sooner or later, maybe in 2 weeks, maybe in 3 months, but you don't want that. Put on a shelf in a working condition, and then 1 month later we took it down, and it didn't work. And then we opened it, looked on the microscope, and the connectors where gold was touching tin were all black. Okay, so then we came up more or less in August or September last year, FM, which was built nicely, and engineering qualification model, which has experienced all these tortures. This was kind of ready. And then we went to integrate things, and we discovered that our nice CubeSat was not fitting into the dispenser. You can laugh, but if you are not careful, it will happen to you. Why? Because the whole CubeSat structure and the whole stack connectivity, it's not like the structure is much stronger than the things inside it. Actually, if you are not careful with the space, you can put a lot of stress, things start to bulge out, and you don't need much, because the tolerances which are prescribed by the standard are actually very, very strict. You could not see it with a caliper. So what we ended up doing, we made a template with 100 millimeter 0.15 for the width, and we used the template at each step of the assembly. And then after tightening some screws, using the templates in all 4 directions helped us a lot. If you have a fully standard structure, no deployables inside, you are more lucky to avoid this. But if you have things like our boom, for example, in non-nominal places, you have to be very careful about this. We put it in the dispenser, many nice pictures. This is in Germany, putting everything together. This is already in Russia on Vostochny launch site. So here you can see boxes of CubeSats, one of which is ours, being put together, integrated with the launcher, the Meteor, the Russian weather satellite, and then one of the boxes is our CubeSat. And this is a whole rocket, and it looks very nice, and the launch looked very nice. So 1 year ago, in the morning, I was sitting at GomSpace in Aalborg, very much expectant to receive first signals, but we didn't, because this was a launch failure. And all 18 satellites on that launch disintegrated, and this kind of the final stages of re-entry. So everything is already disintegrated. The launch failure itself is a bit interesting because it was finally tracked down to a software error which had to do with the algorithm of the Fregat. The fourth stage is a Fregat which is like orbital tug, which can do fantastic things. It can fire up to like 20 times and can put satellites in different orbits. When the three first stages work nominally and brought Fregat where it should be, the first step of it is to check attitude. And usually it is a few degrees which it has to correct itself. And the algorithm works in angles. Yeah? If you have angles, you always have some kind of singularity. For example, you expect that to be 3 degrees and you read out 359. You understand the 4-degree error. You should go over 0. But if the algorithm is not geared to that, it will go the long way. And that's exactly what happened. So the error was really very small, but it was on the other side of singularity, and it decided to go a long way around. By the time it reached next firing, it managed to reorient itself by almost 180 degrees. So instead of raising the orbit, it actually sunk the orbit. This is one of the sad movies I wanted to show you. So you can first see here, this is the launch site of Vostochny, and then this was supposed to be the orbit, and it was actually beautiful aurora this morning. But the sad thing will come here. See? This is the Fregat starting to burn as it re-enters. This was filmed from an aircraft, transatlantic aircraft somewhere southwest of Iceland. And this kind of the final stages of re-entry. So everything is already disintegrated. So as someone was telling over lunch, very low orbit. Yes? Try beating that. Okay, so I'll start wrapping up here and do some advertisement, or at least something we can boast with. Back to your question, GomSpace has made a 3U panel with 20% more power. So you have not 6, but 8 cells on the side. But it's deployable. It's not body-mounted, it's deployable. And it actually has cells on both sides. So it's a very useful thing for the power budget. Another thing GomSpace did by our forcing is a non-magnetic battery pack. It's very good for us because it's non-magnetic. The P60 power supply was developed pretty much with requirements of SIEM in mind, so this drove this development. This TCM was an intermediate step from the earlier mass memory at OAC Microtech toward the new product. So this was built on the previous architecture, but the usage is the same. So the model of having mass memory coupled with the CCSDS protocol partly implemented in hardware, this was a very useful thing, which they took further and developed the new products, which they call Sirius, and then they went to higher frequencies, so they can go to X-band modulators, higher data rates, and also they use a space wire. Now, my 2 final slides here, what lessons I learned, I would split it into technical and management. So technical, it is extremely important to have system engineering at the early stage, so that everything is designed and thought through and not left to a chance. And we had a guy at GomSpace, and it was really invaluable. Whenever you have things which are done in different places, you have to test early, because this is a high risk at integration. Things will definitely go wrong, something which you should think early and test as early as possible. And interface definition is not the whole story. It is important to have it, but it's also important to test. An early flat-sat test is critical. And another obvious thing, subsystems must be reprogrammable in the assembled state, because this is a huge hassle to deassemble half of the satellite. And then these management lessons from SIEM, the qualification testing scope. So when you have a new system and you need to qualify it, This effort was heavily underestimated in our project. This took much more time than we expected. The same thing with software development. Somehow it has fallen between the chairs when we were writing the proposal. And the other thing, it is very important to have continuity of engineering stuff, and it's very important to keep the commitment of the management, of the executives. Because if you lack any of those, or in the worst case both, it is extremely difficult. It can, however, be remedied to some extent by documentation. So keeping documentation at each stage, even if it seems like a waste of time, technical documentation has to be done, because people will quit, move jobs and so on, and then you will have double trouble reverse engineering everything. That's what I had to say. The SIEM story is not over. We're trying to refly the EQM, but that's a separate story, and I will not be telling any of you before it flies. Okay? Thank you.